I'm going to say here that just in case any computer scientist happened to wander into this video, hello, I don't know why you're here, but thanks for showing up. I'm going to apologize to you in advance, though. It's been a long time since I took computer science, and I'm not making this for people who are taking computer science or have any real intent to. So, probably going to get some details wrong, and even if I don't, I'm going to really oversimplify things to the point of maybe butchering them. And I'm so very sorry, but this video wasn't for you. I'm trying to make things interesting for people who otherwise might not give it a chance. Anyway, we're talking about binary. What binary is a system that on its face looks very simple. It's just ones and zeros. Something or nothing. Yes or no. On or off. So, if we're looking at a binary number, something like what we have here, 0, 1, 0, 1, 1, 0, 0, 1, you see that, and, well, in your head, the first thing you might want to do is lop off that first 0 there and be very confident to yourself that that's, what would that end up being? 1,011,001? But for one, you should, well, be careful of that. Because even though generally speaking we talk about things in terms of base 10, we don't have to. And it being binary means that that's actually a very different value. And two, you're probably wondering why that 0 is there, and I'll talk about it in a second. But what we need to notice when we're thinking of things in other bases is that each of our digits, just like each of those groupings of symbols in the last section corresponded to an amount of 60s or 360s, each of those digits here will instead represent an amount of 2s in the binary system. Where that first one, because it's the furthest over, we're following the sort of scheme that we use in Hindu Arabic for this, thankfully. That one, because it is all the way 7 places over, will be a 2 to the 7th. Then the next is a 2 to the 6th, to the 5th, 4th, 3rd, 2nd, 1st, and 0th, the 9th power, as it were. Where because there are 0 in that far one over, it's 0 of them, then we have 1 to the 6th, 0 to the 5th, 1 to the 4th, or 16, 2 cubed, or not 2 cubes, 1 2 cube, or 8, and then finally all the way down there we have 1 2 to the 0, which would end up just being 1. So if we want to translate that, thinking in terms of each of our separate pieces, each of our digits, we would get a decimal, a base 10 value of 89. And if we wanted to be sure, breaking that up so we could see it actually properly as a full equation, we would get functionally the same thing broken down into slightly different steps, where sometimes, just to be sure that we're actually referring to the things that we want to, if, in this case, because this is a binary value, we want to identify that this is in base 2, so you write a little subscript with the number for the number base, where we could say that this value, 0, 1, 0, 1, 1, 0, 0, 1, there's a nice rhythm to it, doesn't it, is equal to 89 in base 10. And often we won't be writing that subscript 10 because base 10 is generally considered the default. It's the default for the number system we're using, but for clarity, I included it there, and I'll probably include it in another example when it comes up, just so you know. And you're probably thinking, okay, great, that's how you do the conversion. You said you weren't going to do math, so you're going to talk about history, and I will talk about history. It's patient. The reason why I chose binary in particular, and the reason why I said binary matters, is because binary is essentially the language of computers.
You get used to it. I don't even see the code.
And the reason why it's the language of computers is, if you think all the way back to what a computer is at its most basic, it's a set of electrical components. And when you're talking about an electrical component, yes, we're at the point where we have dimmer switches. But for the most part, it has two positions, on or off. We're going to think of 0 as being something like on, and 1 is something like being off. So when we're talking about our binary digits, which in computer language they abbreviate as bits, we're essentially thinking of a series of on-off switches, a series of lights that go on and do various different things that we can handle, where in particular if we have 8 of these bits, and that's why I included 0 here, even though it's technically an off, and we don't always include zeros, that is what we call a byte. We have 8 bits. You get a byte, but probably when you hear 8 bits, your head might jump in and start getting visions of Italian plumbers and turtle shells and very angry monsters and weird power-ups contained in mushrooms. But that is the story that we're talking about. And in particular, in video games, it used to be that for every pixel, you had 8 bits of color, which is where that name came from, the old Nintendo Entertainment System games. And every single pixel, you had 8 choices in there with 2 options in each choice. So those of you who have taken stats or are aware of fundamental counting would know that is 2 raised to the 8th power, or 256 possible colors. Then moving on to a little bit more modern, the 64-bit systems for that representation. You had 2 to the 64 options per pixel, so you had a bit more advanced graphics. And getting to now, that idea of bits doesn't have quite the same meaning, and we obviously have slightly prettier pictures, but you get the idea for how these things have advanced in terms of our bits and our bytes. Thought this might be a nice little bit of context for you all for how these pieces came together, where they came from, and in particular for us, why we might care about values that aren't just in our nice base 10, where these things might still be used today. But anyway, next thing we're going to do is look at how we can handle more things in this vein, and this idea of converting from one system to another, in particular converting around base 10.